First of all, I know that you're all busy people and that your time is valuable. So I will do my very best to make this presentation both educative and interesting. My name is Tobias Larsson, and I'm currently working as Business Development Manager for Outokumpu's operations in the Middle East. Just to make it clear from the beginning, this is not a typical sales presentation. The objective with this presentation is to briefly share our knowledge and expertise in 3 different areas, and how each of them can contribute to a more cost-effective and sustainable solution. And these 3 different areas are Duplex stainless steel, our atmospheric corrosion testing program, and stainless steel used as reinforcement bar. The first one up is the duplex stainless steel, and some of you might be familiar with it already, but if you're not, I will try to explain it in a short and simple way. The definition in terms of alloys of normal steel is iron plus carbon. Then it's actually the chromium that gives the stainless steel its basic corrosion resistance, and the chromium promotes a so-called ferritic microstructure. Then, when you also add nickel, you increase the ductility and toughness of the material, so you make it easier to form. And the nickel promotes a so-called austenitic microstructure. Duplex is then a homogeneous microstructure that takes the best characteristics from the ferritic phase mixed with the best characteristics from the austenitic phase. The number one reason why duplex is growing rapidly today is because of the high strength. So in order to get the same strength, you would need this amount of material of the austenitic stainless steel, while you only need this amount of material with the corresponding duplex stainless steel. So don't get fooled by the thin arm on the right-hand side, because it is indeed very, very strong. Taking a look at some of the most common grades in the 2 families, where we have the yield strength on the vertical axis and the corrosion resistance on the horizontal axis. As you can see, in terms of corrosion resistance, they are on a quite similar level, even though the corresponding duplex grade in most cases performs a bit better. Taking the lean duplex grade called LDX2101 as an example, this grade can normally substitute the austenitic grade 304, but in some applications it can also substitute the 316 grade. But as you can see, the biggest difference between the 2 families is the strength. Taking a look at the chemical composition of the austenitic grade 304 compared with the lean duplex grade LDX2101, you can see that we have substituted the expensive nickel with molybdenum, manganese, and nitrogen, which all are cheap in comparison with nickel except for the molybdenum, but this is in small amounts. So it has a good corrosion resistance thanks to the high chromium content, and it's been further optimized with the other alloys. Now we'll take a look at a theoretical example in the shape of a stainless steel storage tank. Here we have a storage tank that is 18 meters high and with a diameter of 18 meters as well. The light blue staples represents the wall thickness of the austenitic grade 304, and the dark blue staples represents the wall thickness of the duplex grade LDX2101. So in the austenitic case, starting from the bottom of the tank, you will have to use a thickness of 12 millimeters, going to 11 millimeters, 9 millimeters, 8 millimeters, 7, and then 5 millimeter in the upper part. While in the duplex case, you can start with a wall thickness that goes from 7 millimeters, 6 millimeters, and then 5 millimeters for the upper part of the tank. And the reason why you cannot save anything in the upper part is because of the design rules of stability and such. So in this case, just by substituting the austenitic grade for a duplex grade, you will have a weight saving of approximately 30%. Now looking at some real-life examples of applications utilizing the duplex characteristics. The first one up is the Cala Galdana Bridge that was opened in 2005, then as the first road bridge in Europe and probably the world, using stainless steel for its load-bearing structure. It has a span of 55 meters and is 30 meters wide, The main structure of the bridge is entirely in stainless steel and includes 2 parallel arcs, 2 longitudinal beams, and transverse beams supporting the deck. Reinforced concrete makes up the abutments at each end, which sit on piled foundations. Before the stainless steel bridge, a reinforced concrete bridge spanned this river for 30 years, but the marine atmosphere led to significant deterioration of the structure. A highly durable material was then required for the bridge structure in order to achieve a long life with low maintenance. Because of the importance of revenue from tourism in this area, a material which blends in with the natural surroundings and causes minimal disruption during construction was required. These were the initial steel grades considered for the bridge. You have the carbon steel called S355, you have the Austenitic stainless steel 316, and you have the duplex stainless steel 2205. The final choice became the duplex stainless steel grade 2205 with the minimum yield strength according to the standard of 460 megapascal. However, the actual values received were a lot higher. Other important criteria except the strength were corrosion resistance, low maintenance, and easy and quick assembly. So in order to meet the criteria of easy and fast erection, Outokumpu supplied about 1,000 bridge components, plasma cut, according to drawings, edge prepared, and ready for welding and assembly in the bridge builder's workshop. Here we can see the assembly of the load-bearing structure from the prefabricated segments. And each detail had a specific reference number so that the contractor could put it together more or less like a puzzle. Another great example is the Stonecutters Bridge in Hong Kong, which opened for traffic in December 2009. It has a design life of 120 years, and it's the upper 120 meter of the pylons, which is cladded with 20 millimeter thick duplex stainless steel. Inside these pylons, you can also find reinforced concrete using stainless steel reinforcement bar, which I will come back to later in the presentation. The reasons why they chose duplex stainless steel was, number one, because of the high strength, which meant that they could decrease the thickness and thereby have less material, which of course meant cost savings, but also easier handling when erecting the structure. Second is because of the corrosion resistance, to suit the marine environment, which is hot and humid. And there's also a high amount of chlorides in the sea. The third, because of the minimum or no maintenance, since the rain will naturally clean the pylon. And aesthetic appearance, that the material looks good and shiny for a long time. Here you can see a concept view of the 3-lane high-level cable stay bridge, which has a total length of 1.6 kilometers and a clear span of more than 1 kilometer. The next one is the Singapore Marina Bay Bridge, which has a design life of 100 years, and it was inaugurated in April 2010. It is 280 meters long and 6 meters wide, and it links the bayfront area and Marina Center in Singapore. Its double helix is composed of 2 spiraling tubular stainless steel, and it is supposed to remind us of a human being's DNA. They also chose duplex stainless steel for more or less the same reasons as for the Stonecutters Bridge. So once again, because of the high strength, the excellent corrosion resistance, no or minimal maintenance, and the aesthetics. This is the same bridge in the evening time. Then we have the latest one, which is the King Abdullah Aziz Knowledge Center in Saudi Arabia, which will mark the 75th anniversary of Saudi Aramco. It was originally designed in the Austenitic grade 316L, but after meetings with several stakeholders, they were convinced that Duplex 2205 was the right choice for this application and location. It's actually pipes located very close to each other that forms the facade. And as you can see, there are people in the bottom of the picture giving an indication of the building's impressive size. The stainless steel facade will also serve as a ventilated solar shield against the harsh Saudi Arabian sun. The building is currently under construction and is expected to be finished in the beginning of 2013. The second part of this presentation will be about our atmospheric corrosion program. How many of you listening think that the Middle East and Europe has the same atmospheric conditions? I guess most of you agree that we don't. So why do we then tend to specify the same material? I think the major explanations are that number one, there is no historical data or experience from the Middle Eastern region. Number two, many of the specifiers are still based in Europe or the US. We currently have over 500 samples exposed in the UK at various sites and hundreds of test panels in the US. But most of our atmospheric corrosion test data concerns austenitic and ferritic grades exposed in European environments. So the aim with our new atmospheric corrosion program is to supplement our knowledge with atmospheric corrosion testing in non-European environments. We currently have exposures at 5 new locations. On the west coast of Sweden, which is a marine site. On the east coast of Australia, Brisbane, which is also a marine site. We have an urban site in China, Beijing. We have an industrial site in Saudi Arabia. And then we have 2 sites in the UAE, 1 marine and 1 desert. And we're also in the process of starting additional test sites in both Kuwait and Qatar. So currently in Dubai, we have more than 500 samples. And today I will show you the results from the marine location, which has been exposed for a bit more than 2 years now. But here we can see a carbon steel sample that has been exposed in a European marine environment since 1990, so around 20 years. And as you can see, it has more or less totally corroded away. If we then look at the austenitic grade 316, which have been exposed for almost 50 years, and it still looks pretty good except for some small staining. You can also see from this picture that the sample in the open condition performs a bit better than the one in a sheltered condition. And the reason for that is that in Europe we have the rain that naturally cleans the material. Here's a picture from Google Earth showing where our 4 racks are located, and they are approximately 50 meters away from the Gulf. We are doing this research project together with Dubai Electricity and Water Authority. In total we have 4 racks where 2 are open and fully exposed and 2 are in a sheltered condition. So this is how the samples looked like when we started the testing on the 12th of May 2010. You can see in the bottom right corner that on some samples we have also drilled a hole to form a so-called crevice, and on some we also have a weld to see what impact this has on the atmospheric corrosion resistance. The samples on the bottom row acts as reference samples such as carbon steel, aluminium, zinc, and copper. And now you will see the same rack after 3 months exposure. As you can see, the rack is completely covered with dust, and the carbon steel, aluminium, zinc, and copper are facing significant surface corrosion already. And now we're going to take a look and see how the various stainless steel grade performs. Here you can see the austenitic grade 316 with a cold rolled finish, so-called 2B. This is the same grade as we saw earlier that performed well in a European marine environment after 50 years exposure. And this is the same sample after 3 months. It does not look pretty. So actually this grade performs worse in a Middle Eastern marine environment after 3 months than it does in a European one after 50 years. You can also see that here we have the other way around compared to Europe. Here the sheltered sample performs better since it is covered from the dust and the airborne chlorides from the sea. And in the Middle East we don't have the rain that naturally cleans the material. Here we have the same grade but with a bright annealed surface finish, which is almost like a mirror, because the smoother surface finish, the better corrosion resistance. It is a bit difficult to see from the 3 months results since we did not brush off the dust, but it has a visible light corrosion. However, we can clearly see from the 12 months results that the 316 is not good enough, not even with the bright annealed surface finish. So what do we do then? Well, we need to move up the chain in terms of corrosion resistance. And since we want to find the most cost-effective solution, we will take a look at the duplex grade known as 2205. Well, even the 2205 with the bright annealed surface finish shows some small staining. However, with a sound cleaning program, this grade would probably be good enough. We should also remember that this is one of the most severe locations in the world, and when we evaluated the first 3 months of our test site or inland, it did not show any staining for the 2205. So we can clearly see from the 21 months results that the duplex grade 2205 performs better than the Austenitic grade 316. But what if you want to specify a material in a marine Middle Eastern environment that undergoes no or very little maintenance or cleaning? Well, you probably then have to go for the super duplex grade 2507 or the super Austenitic grade 254 SMO in order to have an aesthetic structure with a long design life with little or no maintenance. However, the leap in cost from 2205 to 2507 is quite substantial. So in most cases, 2205 with a suitable cleaning program is the most cost-effective solution. As you can see, there are no visible attacks on the duplex 2507 nor the Austenitic 254 SMO after 12 months exposure. Why is this the case then? Well, I've listed some of the most common reasons, and I won't go into too much details, but condensation and humidity is one factor, and corrosion can only take place when moisture is present on the surface. You normally talk about this period as the time of wetness, and when you don't have any chlorides present, the time of wetness is defined as the period of time when the temperature is above 0 degrees and the relative humidity is above 80%. When there is accumulation of surface deposits that retain moisture, the time of wetness can be much longer. When chlorides are present, this can begin to occur at 0 degrees and humidity level of 45%. Lack of cleaning rain is also a factor, since the material will never be naturally cleaned as in Europe. The dust will retain the moisture for a longer time and can create so-called deposits. The salt concentration, i.e. the chlorides, are the single biggest factor, since the chlorides are stainless steel's biggest corrosion enemy. And as you probably know, the salt concentration in the Gulf is considerably higher than most other oceans in the world. The high temperature also has a tendency to speed up the initiated corrosion process. And last but not least, the short distance to the sea makes it a very aggressive environment. So how to solve the problem then? Well, it is possible to use stainless steel in an aggressive coastal environment, but today's normally specified 316 grade is not the right choice, and there is a growing awareness of the problems among the local companies here in the Middle East. So first of all, you need to choose the right grade of stainless steel. Then you should try to have as smooth surface finish as possible. A cleaning program is very important since we don't have the rain that naturally cleans the material. You should also try to avoid crevices, since these are created by high levels of dust, sand, industrial particulates, and even leaves, and this is not always considered during site assessments, even though corrosion is more likely to initiate in these areas. And finally, you should always clean and treat your welds properly. Now let's have a look at the third steel used as reinforcement bar. In the US, the estimated annual direct cost of corrosion of bridges is somewhere around $5.9 billion to $9.7 billion. However, I have seen figures as high as $300 billion, eating away 3 to 4% of the total GDP. As much as 40% of this is estimated to be preventable. In Western Europe, approximately 5 billion euros is spent yearly for repair of corroding concrete structures. And according to an article in the Saudi Gazette, where people from Saudi Aramco, SABIC, and various universities has made an estimate that approximately 2 billion Saudi riyals is linked to deterioration of concrete in Saudi Arabia. Here we have the Progreso Pier in Mexico. To the right, we have a pier built in the 1940s using stainless steel only as reinforcement bar, so no carbon steel rebar. And to the left, we can see the remaining of a pier built in the late 1960s using carbon steel rebar, and it failed after less than 30 years in service. According to the Progreso Port authorities, the pier has not undergone any major repair work during its lifetime, and there has been a complete lack of routine maintenance activities. Since the way forward for successful companies is to find the most cost-effective solutions, our advice is to use stainless steel rebar selectively in the most critical areas. In this case, for the Gateway Bridge in Brisbane, Australia, it was used in the outer layer of the bridge piers, located in the sea. So in total, 130 tons of stainless steel rebar out of a total number of 7,800 tons of rebar used was specified in stainless steel. And by doing so, the design life of the bridge was increased from originally 100 years to around 300 years. So you can imagine the effect it had on the total life cycle cost of this project. If you take a look at the current standards for concrete structures, even the British standard states that there is a degree of uncertainty. It states the following: there is a degree of uncertainty with the recommendations for an intended working life of at least 100 years in the chloride and seawater environments. Reliance solely on cover and concrete quality might not be the most economic solution. In these situations, consideration may be given to using other techniques such as stainless steel or non-ferrous reinforcement, barriers, coatings, and corrosion inhibitors. There is also a specific guide to the design of concrete structures in the Arabian Peninsula. So for normal structures with a design life up to a maximum of 30 years and generally in more benign inland conditions, the durability solution is to use the normal prescriptive tablets measures. However, if you have a special structure defined as with the design life greater than 30 years and structures in extreme exposure conditions, the durability solution is to make a project-specific durability study where additional enhancement techniques are likely to be required. We therefore promote the use of so-called predictive modeling, which is a way of assessing the level of chlorides in the concrete at depth and with time. So when you are using predictive modeling, you will have to know the steel grade's critical chloride threshold level, CCTL, which is the amount of chlorides that the steel can withstand without starting to corrode. We are using a so-called in-solution potentiostatic method. As you can see, just by choosing stainless steel, you will have a critical chloride threshold level about 10 times greater than that of carbon steel. The Austenitic grade 316 and the lean duplex grades LDX 2101 and 2304 performs more or less on the same level, while the 304 values are a bit lower. However, you can also see that there is a big scatter in the results. Therefore, we think it is better to use the idea of probability. This graph shows that there is a 90% probability of LDX 2101, 316L, and 2304 rebar achieving a critical chloride threshold level given about 6% chlorides by mass of cement. And this figure drops to about 2% for the 304L. So which one do you then choose if they perform more or less on the same level? Well, it's quite easy. You take cheapest and most stable one in terms of price. With the entrance of the lean duplex grades, the interest in using stainless steel as concrete reinforcement has increased substantially, since the perception has always been that stainless steel is too expensive. So reaching the end of this presentation, I just want to emphasize that in order for us to change something, we need to act together. We need to change our behavior so that we act more long-term and not just think about our current budgets, even though this is extremely hard in today's business climate. Because if we do this, then we will have much more cost-effective and sustainable structures. Just before ending, I would just like to mention that Outokumpu once again has been given the highest environmental scoring among the steel industry by the Dow Jones Sustainability Index. And we can also now, as the first supplier of stainless steel in the market, provide so-called environmental product declarations, where a life cycle analysis is carried out so that you receive input to ratings such as LEED, BREEAM, and similar green building ratings. Building today for generations to come. I hope this presentation gave you a brief overview of the three topics. And if you have any questions, you are most welcome to email me, or you can take contact with your local Outokumpu sales office. Have a great day.